Have you ever wondered what happens when a star's life reaches its epic finale? Stars don't just fade away, they go out with a spectacular bang, creating some of the most awe-inspiring events in the universe. Supernovae are cosmic explosions that light up galaxies, forge heavy elements, and sometimes even birth black holes. Curious about the science behind these stellar fireworks? Join us as we unravel the mysteries of supernovae, diving deep into how stars meet their dramatic end and leave a lasting impact on the universe. Let's embark on this cosmic journey together. The life cycle of stars from birth to death. Stars are born from immense clouds of gas and dust called nebulae. These cosmic nurseries condense under gravity, igniting nuclear fusion and giving birth to a star. Over millions or even billions of years, stars burn hydrogen into helium, balancing the outward pressure of radiation with the inward pull of gravity. This balance is what keeps a star stable during its lifetime. As a star ages, it runs out of hydrogen fuel, and its core contracts while the outer layers expand, transforming into a red giant or a supergiant depending on its mass. For stars like our Sun, this marks the beginning of a quieter end, eventually becoming white dwarfs. But for massive stars, the story takes a far more dramatic turn. These giants are destined for a catastrophic explosion, their deaths creating supernovae that are visible across galaxies. The mass of the star determines its fate. Stars 8 times the mass of the Sun or more experience core collapse, where gravity overcomes the core's resistance, triggering a colossal release of energy. This explosion can briefly outshine entire galaxies. It's during these final moments that the heaviest elements in the universe, like gold and uranium, are forged, enriching the cosmos with the building blocks of planets and life. These explosive endings aren't just about destruction. They serve as the universe's recycling system, spreading heavy elements into space and seeding the formation of new stars, planets, and even life itself. Without supernovae, the universe as we know it wouldn't exist. Core collapse supernovae when gravity wins. Massive stars live fast and die young, burning through their fuel quickly. Once the fusion of heavier elements like iron begins in the core, the star's fate is sealed. Iron cannot produce energy through fusion, leading to a catastrophic collapse. The core compresses to an incredibly dense state, and the outer layers are hurled into space at incredible speeds. The energy released in a core collapse supernova is almost unimaginable. For a brief moment, the dying star radiates as much energy as our Sun would emit in its entire lifetime. This explosion sends shockwaves ripping through space, creating stunningly beautiful remnants like the Crab Nebula. The core left behind can become either a neutron star or a black hole, depending on its mass. Neutron stars are incredibly dense, with a teaspoon of their material weighing billions of tons. Black holes, on the other hand, are regions of space so dense that not even light can escape their gravitational pull. Both are the remnants of a star's extraordinary life and death. These supernovae are not just celestial spectacles, they play a crucial role in galactic ecosystems. The shockwaves from the explosion compress nearby gas clouds, triggering the birth of new stars. In this way, the death of one star leads to the creation of many more, continuing the cycle of cosmic life. Type Ia Supernovae, the explosions of binary systems. Not all supernovae result from massive stars. Type Ia Supernovae occur in binary systems where one star is a white dwarf, the dense remnant of a star like our Sun. These explosions are triggered when the white dwarf accretes matter from its companion star, reaching a critical mass. At this tipping point, the white dwarf undergoes a runaway thermonuclear reaction, detonating in a spectacular explosion. Unlike core collapse supernovae, Type Ia Supernovae leave no remnants like neutron stars or black holes. Instead, they completely obliterate the white dwarf, scattering its material into space. Type Ia supernovae are particularly valuable to astronomers. Their consistent brightness allows them to be used as standard candles to measure cosmic distances. These measurements have helped scientists discover the accelerating expansion of the universe, leading to the groundbreaking concept of dark energy. The elements produced in these explosions, including iron and nickel, enrich the interstellar medium, contributing to the formation of new stars and planets. Without Type Ia Supernovae, the universe would lack many of the elements crucial for life. The role of supernovae in cosmic evolution. Supernovae are more than just the dramatic end of a star's life. They are cosmic catalysts driving the evolution of galaxies and the universe itself. The heavy elements produced in these explosions are the building blocks of planets, moons, and even living organisms. The shock waves from supernovae shape the structure of galaxies by compressing gas clouds, triggering new waves of star formation. Over billions of years, these explosions have transformed galaxies into the dynamic, complex systems we see today. Supernovae also influence the interstellar medium, creating stunning nebulae that serve as birthplaces for future stars. The famous pillars of creation in the Eagle Nebula, for example, are shaped by the shock waves of past supernovae. Without these stellar explosions, the universe would be a much quieter and less diverse place. From forging heavy elements to shaping galaxies, supernovae are fundamental to the story of the universe. They are the bridge between the death of one generation of stars and the birth of the next, ensuring the cosmos remains vibrant and ever-changing. Supernova remnants, the aftermath of cosmic explosions. The remnants left behind by supernova are some of the most fascinating and visually stunning structures in the universe. These are vast clouds of gas and dust, glowing with the light of ionized particles energized by the explosion. The Crab Nebula, for instance, is a famous example of a supernova remnant that has captivated astronomers for centuries. These remnants are more than just pretty sights. They are crucial to the chemical evolution of galaxies. The intense heat and pressure from the explosion create and disperse heavy elements like oxygen, carbon, and silicon, key ingredients for planets and life. These elements mix with interstellar gas and dust, enriching the material that will form future stars and solar systems. Remnants also emit a range of electromagnetic radiation, from visible light to X-rays and radio waves. This radiation provides astronomers with valuable information about the composition and dynamics of the explosion. By studying supernova remnants, scientists can piece together the life stories of stars and the conditions that led to their spectacular ends. The remnants of supernovae act as cosmic laboratories, helping researchers understand fundamental physics. From studying the behavior of matter under extreme conditions, to understanding the processes that shape galaxies, these remnants are a treasure trove of knowledge. Hypernovae, when stars go out in style. For the most massive stars in the universe, a regular supernova is not enough. These colossal stars, with masses more than 30 times that of the Sun, can end their lives in hypernovae, explosions that release 10 times more energy than a typical supernova. Hypernovae are triggered when a star collapses into a black hole instead of a neutron star. During this collapse, jets of energy shoot out from the poles of the star at near-light speed, creating gamma-ray bursts, the brightest events in the universe. These bursts can be detected billions of light-years away, providing a window into the distant cosmos. The energy released in a hypernova is so immense that it can reshape the environment of an entire galaxy. These explosions are thought to play a role in triggering new star formation on a grand scale. They also produce even heavier elements like gold and platinum, enriching the universe in ways regular supernovae cannot. Hypernovae remain one of the least understood phenomena in astrophysics. Scientists continue to study these extraordinary explosions, hoping to unlock their secrets and understand their impact on the evolution of galaxies and the universe. The role of neutrinos in supernovae. When a supernova occurs, it's not just light and heavy elements that are released. A massive wave of neutrinos, nearly massless particles, is emitted in the process. In fact, most of the energy from a supernova is carried away by these elusive particles which travel across the universe almost undisturbed. Neutrinos are produced during the collapse of the star's core, as protons and electrons are squeezed together to form neutrons. These particles escape the dense core long before the shockwave reaches the surface of the star, providing a kind of early warning signal for supernovae. The detection of neutrinos from a supernova offers critical insights into the explosion's inner workings. For example, the neutrinos detected from supernova 1987A gave scientists their first direct evidence of core collapse, confirming decades of theoretical predictions. Studying neutrinos from supernovae continues to be a frontier in astrophysics. These tiny particles could hold answers to some of the universe's biggest mysteries, from the nature of dark matter to the processes that drive the death of massive stars. Supernovae and black holes, a stellar finale. Some of the most massive stars don't leave behind a neutron star. Instead, they collapse directly into a black hole. This process can occur during both supernova and hypernovae, depending on the mass of the star and the dynamics of the explosion. When a black hole forms, it exerts an immense gravitational pull on its surroundings, often drawing in material from its environment. This accretion process can create spectacular jets of energy that radiate across the universe, sometimes forming what's known as an active galactic nucleus. The connection between supernovae and black holes is a subject of intense study. Scientists are trying to determine the exact conditions that lead to black hole formation and how these objects influence their surroundings. Observing supernovae that produce black holes helps researchers understand the relationship between these stellar events and the creation of these cosmic enigmas. Black holes formed by supernovae are not just endpoints, they are the beginning of a new chapter in the life of the universe. These objects are vital to the evolution of galaxies and may even hold clues to the fundamental nature of space and time. Supernovae in human history and culture. Supernovae have not only shaped the cosmos but also captured the imagination of humans throughout history. Bright supernovae have been recorded by ancient civilizations, from the Chinese astronomers who documented the appearance of the Crab Nebula in 1054 to the supernova observed by Tycho Brahe in 1572, which challenged existing views of the cosmos. These celestial events were often seen as omens, marking significant events or changes. In some cultures they were interpreted as messages from the gods or the birth of new stars. Modern science has demystified these phenomena, but their impact on culture and history remains profound. Supernovae have inspired countless works of art, literature, and even music. They remind us of the immense power and beauty of the universe, sparking curiosity and awe. Their role in creating the elements that make up our bodies and the world around us adds a personal connection to these distant cosmic events. The study of supernovae bridges the gap between science and the human experience, connecting us to the stars in ways both literal and poetic. These explosions, both destructive and creative, continue to inspire wonder and a deeper understanding of our place in the cosmos. And there you have it, the incredible science and wonder of supernovae. These cosmic events remind us that even in death, stars contribute to the beauty and complexity of the universe. If you enjoyed this journey through the cosmos, don't forget to like, share, and subscribe to InnoVision Tech. Hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the mysteries of the universe with us. See you soon.